Welcome back. We have a fun session for you today on how to use the Pennylane platform. And you'll be using this for some of your assignments and the quizzes this year. So we're very excited to welcome Dr. Ben Lau from Xanadu to talk about how to use Pennylane. So Ben works closely with the quantum software team at Xanadu and supports the many external collaborations and projects that Xanadu engages in. Before joining Xanadu, Ben completed his PhD in experimental condensed matter physics at the University of Toronto, studying metallical systems with unconventional behaviors. And we're very excited to welcome him to the program.
Awesome. Thank you, Abhinav. So now I'm going to steal the screen and share it. All right. So thank you again to Womanium for organizing this and inviting Xanadu. Today, I'm going to give an introduction to Pennylane, and it's going to be something to help you fall in love with Pennylane. We're not going to go too deep, but I want to have some key takeaways so that you can understand and not be afraid of actually using it. So we'll start off with the agenda today. I'm going to give an intro to those who are unfamiliar with Xanadu and Pennylane, our software library, and then follow up with Pennylane basics and some live coding. And to look forward to that, I'm going to say if anyone's already familiar with Google Colab, which is an online notebook environment to program in, boot it up, just have it on a second tab maybe, and then we can move on to the demo part a lot more smoothly after that. If you're not familiar, at least make sure you have a Google or Gmail account or some kind of programming environment ready, and we can probably transition to that pretty easily. So I already got an introduction nicely from Abhinaya. I'm Ben, and I'm a technical engagement manager at Xanadu. I work closely with our software teams, and my background is a physics background, an experimental one, where I did a little programming here and there, but mostly with my hands inside a lab. And I did this at the University of Toronto, where we're situated. And yeah, it was a really, really fun time, and I'm glad to be in the physics environment still. So we'll begin with an introduction to Xanadu and Pennylane. And at Xanadu, our mission is to build quantum computers that are useful and available to people everywhere. Useful and available, being real, doing the real work around here. We want to not just make a quantum computer, but let people use it and let it be accessible to those trying to use it. We were founded in 2016 and we're headquartered in Toronto, Canada. And now worldwide, we employ over 240 plus people. If you're curious about learning more, find us at xanadu.ai for our website or on X with our X handle. Now, to give you a little bit of context of what we're trying to do, broadly speaking, is that we don't only work on Pennylane software. Our bigger goal is to have photonic quantum computers. So quantum computers using light. And from our previous years of experience and work, we've developed our core optical components in order to enable this. And moving on from that into, say, the more mature parts of our hardware roadmap, we have a prototype of quantum computer that's modular, networkable, and can thus scale very nicely. And once we master optical loss or photon loss, we can actually scale up towards a fault-tolerant quantum computing data center. And that's in our future roadmap. And that's really where the context of all this comes from, is that we're building on quantum hardware, which then needs to be utilized. And so that naturally begs the question, well, what are the applications and how can quantum computing be used? For us, what we're looking at is quantum chemistry primarily and quantum machine learning. Now, those aren't strictly the only applications, but they're the promising ones that we've been working on lately. In terms of quantum chemistry, this can be looking at lithium-ion batteries and their material characteristics to things like quantum sensing applications where we might need more precise spectroscopic simulations and predictions in order to get that next level of an optimization. We can also look at quantum machine learning, which can begin at the level of optimizing quantum circuits, all the way to really asking ourselves a very fundamental question. How can quantum or quantum mechanics and quantum computing be leveraged within the machine learning space to develop a very unique possibility or advantage? And in order to do any of all that within a quantum computer, we need to be able to interact with the quantum computer. And that's where quantum software tooling development begins. We need tools that are required to develop these quantum algorithms and real-world use cases. Without that, we won't be able to communicate with our quantum computer and thus not access our applications. So that's where Pennylane comes in. It's the Xanadu answer to quantum software programming. And we have our individual website, which is pennylane.ai. Lots of online content and supporting documentation on there. And we're also on X with our own handle, Pennylane AI. So for our software mission, it's still within the subset of building useful and available, making quantum computing useful and available to people everywhere. But for software specifically, we're going to target researchers. We want to make it easier for researchers to design, build, and execute these next generation quantum applications. We don't want it to just sit there in, idea land. We want people to be able to play with it very hands-on in a very accessible way. And so in order to do that, we've actually built up our so-called Pennylane ecosystem. And today, we're actually going to focus mostly on the top left here, which is our Pennylane user-friendly Python SDK, and a little bit about Pennylane.ai, where our online documentation exists. But in terms of the various products that we have available, we have complementary things, the more advanced functionalities, such as our Catalyst compiler and our Lightning high-performance quantum simulators, which help optimize the quantum programs that you would write. We also have, moving ahead of myself, our plugins, where we can connect to different kind of frameworks, whether they be software frameworks at the moment, like simulators, or other quantum hardware frameworks, because Pennylane is hardware agnostic. To kind of prove the point of building out a quantum ecosystem for Pennylane, the ecosystem, we are one of the leading open source communities. So we have over 75,000 downloads a month for Pennylane, and we have a very active Pennylane discussion forum with over 15,000 forum posts. In previous Q hacks that we've hosted, we've also had over 10,000 participants, and academically, over 130 university partners are using Pennylane. So now that's a quick intro into who we are and what we do. We're going to move on to Pennylane basics, more the program part of it, perhaps the most hands-on part. So again, another introduction to Pennylane is that I want to emphasize that it's one, open source, and it's a Python library, meaning for physicists out there and a lot of the comp sci and modern programming, it's a very nice, accessible first step into programming in general. And Pennylane is a part of that entire ecosystem, that library. It's also differentiable in the sense that if you want to apply it for machine learning or quantum machine learning, you can actually calculate gradients and derivatives of functions quite naturally. It's supported, and you can train a quantum computer like you would a neural network if that's what you're trying to explore. And finally, it's very modular. So there are things that are more leaning towards classical programming, what you're probably used to, classical if statements, if then else, normal classical functions in Python. That can be tied very naturally into your quantum workflow, which you'll learn more about by defining devices and defining things within functions. And it's very easy to get used to. In order to install Pennylane, again, like any other Python library, you can just pip install it on your terminal, or in our case later, on Google Colab. Another thing that we want to emphasize is that Pennylane is hardware and framework agnostic. So we have plugins for different vendors and different kind of frameworks. You're not locked into any particular one, and we support multiple ones because we believe Pennylane to be useful for all quantum software developers and programmers. In addition to that, there are a lot of popular software libraries that we can interact with and integrate with, which is NumPy for scientific numerical work, PyTorch for any machine learning, and JAX as well for supporting the machine learning and gradient estimation workflow. So now what I'm going to do is I'm going to give you Pennylane 101 and 102. And these are to give you things to focus on before we move on to the hands-on programming part of things, where we go line by line and go through explaining things one by one. So in Pennylane 101, I want you to focus on these three things. What we're building are quantum circuits, which are actually just quantum Python functions. And what quantum circuits are, they're just instructions for the qubits that you're trying to manipulate. And in this case, on the left here, we're having a so-called Rx gate and RY gate, or just operations, if you want to think about it in your head that way. What are you operating on? Well, you're operating on qubits, or in our case, more generically, wires. These receive the instructions, which change wires' properties themselves in the quantum mechanical sense, their superposition and their phase, and so forth. And then how do we run these quantum algorithms on these circuits, and how do we change these qubits? What do we do to them? How do we execute these instructions? Well, in Pennylane, we have these native simulators because you don't have to necessarily interact with quantum hardware right now. It's a little bit hard to find. Can't just go out to your local shop and buy a quantum computer. You typically have to go find specialized time and buy it to use it. So that's why we rely on simulators and backends to run things on. For Pennylane, we have a few. I'll go over them a little bit later. but the focus is here. We have circuits to run instructions, qubits or wires in which we run the instructions on, and then the backends to actually execute things that you want to do. So here I have the anatomy of a simple Pennylane quantum program. On the right is a screenshot of a very familiar, hopefully, Python program. We have our typical importing of a library into your favorite editor, your environment, whatever you want. And all you write is import Pennylane as QML, and then if you want any supporting libraries from that. And then in addition, all the circuits that you build in Pennylane are just going to be functions. So here on the lower arrow here, we have def defining a circuit with 2 input parameters, and then your instructions that follow. That's all it is. Nothing particularly challenging. And all you have to do is equate circuits to Python functions, smush them together, and there you have it. Next thing to look at are your wires, the things that you're actually operating upon. So here we have wires that define the quantum bits that you perform instructions on, and they're defined as how many qubits that you have or how many wires that you have up here, and then which wires you're actually operating upon down here within your quantum circuit itself. Then what you have are your backends. And to define your backend, typical Pythonic kind of way of writing things is that you have a device and you're calling QML, the Pennylane function. And in this case, your backend that you're calling is default qubit with 1 wire, and you're using that with your circuit. Don't worry about the Q node for now. That's coming up in Pennylane 102. But the takeaway here is we're working on in Python. We have wires that are qubits, and we have backends that are defined in our devices. So speaking of devices, Pennylane, that little screenshot you saw earlier, is that we have many built-in simulators for different use cases, for different simulations that you might want to try. The ones that I want to point out for kind of this intro is default qubit and lightning qubit here. The reason being default qubit, very quickly, it can be used for a lot of prototyping and learning capabilities. It's also accessible because it can be run on your laptop. It doesn't need any kind of like specialization in terms of GPUs, specific CPUs, or if you really want to scale up and you have access to high performance computing clusters. The reason why I point out lightning qubit is it's kind of similar, but now you're not working only in Python. You're kind of tunneling through to a C++ backend where you get more performance solutions. You can support more qubits in terms of execution, and you can also work through things faster depending on what your quantum workload actually looks like. Everything else in between, I'm actually going to defer to our Pennylane website where you can learn more about why you might want to choose the other ones, but it's useful if you're trying to look for specific applications and specific workflows that you need to support. So have a look if you're interested, but we're focusing on default and lightning qubit today. All right, so we've graduated from Pennylane 101. I know it's just blurbs so far, but we'll get to live demos, I promise. Is to focus on 3 other ingredients for a quantum program. One is a Q node that I mentioned before. And all this is tying your quantum circuit, the quantum parts, to the device to execute. So you don't necessarily need to tie in any like classical instructions into your expensive quantum computer or quantum simulator. You can kind of isolate and modularize those to tie them together. So in your mind, think quantum nodes attaching a circuit or gluing a circuit to a device. Next, kind of following up from the fact that circuits are Python functions have a return value. And the analogy follows that if a Python function returns to you a value, a quantum circuit returns to you a value as a result of a measurement, a quantum mechanical measurement. So in this case, what we equate are measurements are the return value of a function. And finally is a very useful thing, especially because this program is focused around quantum algorithms, is our templates, which in my mind are subroutines that are pre-encoded or pre-made for your convenience, because it's a very common thing that you might have for a specific quantum workflow. In this case, we have many of them on our website, pennylane.ai, and we can actually just call these as typical APIs within our quantum program. So we're going back to the same thing, the same anatomy, same body of code, and we're looking at the Q nodes now. We have these Q nodes that tie our device and our circuit together in order for it to execute. So really, you would write your Python function, add this QNode decorator, which is tied to the device that you defined above. Then you have measurements, which are the results of your circuit, or equivalently, if you're just thinking program in terms of programming, the return value of your function that you're defining. And then finally, we have these templates, slightly different, more complex code, or complicated code, is that we have for quantum Hamiltonian simulation, the Trotter product template that you can help with your quantum algorithm workflow in this case specifically, quantum simulation or Hamiltonian simulation. So that was a lot to throw at you, especially if you're new to Pennylane and new to quantum computing. But the main takeaways are highlighted here with the same body of code. I want to emphasize that we have an easy to use Python library. Pennylane is really just a pip install and Python import away. And in order to create the backends to run your quantum workflow, it's just defining a device, whether that be real hardware you may or may not have access to, or the Pennylane simulators that are built in already. Then, in order to tie whatever quantum workflow you have to that device, you define a quantum function here using a QNode as glue to target that device. And then to emphasize that we can easily integrate it to the rest of a typical Python or classical workflow, you can do anything you'd normally do or want to do with a function. You can do composition of functions, you can calculate gradients of functions. In the case of Pennylane, it's really nice because it's fully differentiable. We support gradients within our quantum functions as well. So now we move to the slightly more exciting part where errors are bound to be happening, but we're going to move to live coding. So I'm going to switch tabs quickly to Colab. So hopefully you've had a chance to boot up a new tab, go to Google. If you haven't, please try and type this into your browser URL, colab.research.google.com, in order to access this page where we'll be creating a notebook. So in this case, actually create a new one, but if you're just landing on this page now, please go to File, New Notebook in Drive, and then you'll have a clean workspace in a second at least to generate a fresh notebook. Does anyone see this fresh notebook? I guess I'll take a hint from the hosts.
Yeah, it's visible.
Awesome. Thank you, Katie. All right. So I'm going to close away because I have like a little blurb already provided here. But don't worry, we're going line by line. There's nothing down here for me to cheat on. So this is an introduction, a hands-on introduction to quantum computing with Pennylane. We have a little bit of context from before from the slides, but I know that you learned mostly from hands-on, especially with programming. And the task that we're going to focus on here is we're going to get started with Pennylane. We're not going to go too deeply because, you can only do so much without learning yourself, but also we want to focus on the basics to make you comfortable working with it and learning with it. So before we run to Pennylane, we need to learn to walk with Pennylane. Now, the first thing we're going to do, as I promised, it was an easy install, especially in a notebook environment like this on the cloud. We just do pip install Pennylane. And then if you're not familiar with this notebook environment, you can do Shift Enter to run that command. Okay. And while this installs, I'm going to go over the goals, the technical goals, I guess, of our program. We're going to install import Pennylane. And then as a task, we're going to create a so-called bell state, which is a maximally entangled state, or what you can say is like it's the minimal resource that you need to know how to create to start with quantum programming. Then using that bell state, we're going to tie that circuit that creates it to a QNode. We're going to glue it to these quantum devices, these backends, and then we'll return the probability of each of those entangled states and see what comes out. We're going to, because it's just a function we've defined at that point, run the circuit, see what comes out, see if it makes sense, and then end off playing around with some of the backends. So hopefully you've had a chance to run the pip installation. It usually takes about 18 to 30 seconds, depending on how the servers are feeling that day. But you can see all the installation instructions here, installing collected packages, successfully installed, no errors popped up, you're a happy camper. Then what you can follow up with is, well, we move directly into our Python environment. What we can do first is import, whoops, not capital, Pennylane as QML. And you may notice that Pennylane as QML is kind of weird. There's no QML as letters within Pennylane, but for historical reasons, we've built this around quantum machine learning. So we've kept that, and it's a nice thing to always say QML dot whatever you want for any Pennylane instructions. So in this case, this is using Python and importing Pennylane in. Whoop, did I hit a back button? No, I didn't. We're good. And then I'll be commenting this is installing Pennylane. Afterwards, we'll be sharing this notebook around with probably more cleanup comments, but I want to comment as I go, set a good practice, but also to keep anyone who might not be following vocally as well to be able to follow visually on the screen. All right, so I'm going to execute that command, and what you'll notice immediately is a flag, and that's to do with the fact that we're in a Google Colab environment, and sometimes there are some packages that are mismatched with our latest release. But in this case, don't worry about it. We'll be okay. If you get really deep into Pennylane, you may start to think about what are the features that you need to be aware of and kind of version control around that. So we're going to hide that away for now, not too important. And then what we can do as kind of a final check to make sure that we did the right thing is use the built-in function to say, well, what did I actually just install on my computer? What's the version? And what are the supported backends using qml.about? So check installation and import will be the flag here. Shift enter, let it run. And hopefully you get the same thing as me for what's coming out. Is that what did we queue information about? Well, Pennylane, what version of it, which is 41 here, and that's our latest release. We have some information for our GitHub repo, a summary of what it is, but that's all extraneous in terms of this tutorial at the moment. What we want to make sure is that the installed devices that we have access to are the ones that I promised before that we will be focusing on, which is default qubit here and lightning qubit a little bit later. Lots in between, and you can go into the documentation to find out a little bit more about that. All right, so that's about. Let's look at our checklist. We've installed, imported, and checked installation and import. Now what we want to do is start essentially quantum programming. And we always want to define a backend in order for us to execute whatever we want to eventually. And it's part of the workflow. Try and define your devices so that you can tie your circuits through a Q node to it easily. So very easy. We're going to use dev for device, and that's going to be equal to qml.device. Now, what are you going to input into this? Well, the string default qubit. We'll queue whatever backend you want, in this case, default qubit. And then we need to specify the number of qubits or wires that we actually want to support. Because as a minimal example, let's just do 2 to show the creation of a Bell state. Okay, so this creates a device using default qubit as a backend with 2 wires. All right. Now we're going to execute that. Very easy, very quick, nothing strenuous going on. You're kind of essentially allocating what your device is and what you're trying to hit. Then the next thing that you want to do is you want to create a Q node and also a circuit. So define a Q node with a circuit that creates the Bell state. Now, I didn't really explain this above, but this is actually the circuit that we're targeting for those who aren't so used to quantum computing yet. What we have are 2 qubits, qubit 0 and qubit 1, consistent with Python arrays, numbering starting from 0. And what we're going to do is enact the circuit in order to create a Bell state and measure it, which are these kind of like clock-like looking diagrams here. In order to create the Bell state, we actually need to enact a Hadamard gate on the 0th wire, and then a CNOT gate following that to entangle it with the other wire. How you can see this from a quantum mechanics point of view is that the Hadamard gate creates a superposition, and then the CNOT gate creates entanglement, and then the measurement at the end will collapse your qubits. So let's do that, but in Python programming form. So naturally, I actually like to write down my circuit first, because it's like the instructions and the circuit that I'm building, right? So qml.hadamard, if I could spell, and the wires that we want to target. Here, we want to target wire 0, and so I'm going to target wire 0. And then close brackets. for those of you who might be asking, well, why am I using an array in here? It's that sometimes, for different instructions like the C0 gate, we can target more than one wire. And so to do that, you could do something like this later. But out of good practice, I like to make an array even for a single wire target. And the next thing that we need to do is using 0 as a control. We want to target wire 1. Notice this kind of like crosshair looking thing. That's how I memorize it in my own head, is that we want to do a C0 gate on wires equal using 0 as the control and 1 as the target. Close bracket. And you're pretty much done. Now we need to remember that we need to return a measurement at the very end. In this case, we're going to measure the probability of our state, and we're done. We've created our circuit, but we haven't tied it yet though. So what we're going to do all the way back up here is use our QNode decorator, QML.QNode, and tie it to the device that we defined immediately in the cell above it. All these check out, and we're good. Now let's do a little bit of commenting. We're creating a Bell state. Bell state here with the circuit. And so let's do Shift Enter. No errors. I'm very happy to see that. Very quick to run. And the function itself is created. Now the function needs to be executed. But before that, before even all that, perhaps we should make sure before we spend any resources, especially if you have a real quantum computer, that your circuit is actually correct. And Pennylane actually comes with a very handy command, which is to draw out the circuit that you just drew. In this case, let's just call the circuit called circuit, and I'm going to let it draw. Does this match? Yes. And that is what we're looking for. The exact same circuit as the target circuit that I wanted to and sketched out the circuit for in the cell above. Now, what we can do is, this is actually really fun personally, is that we can actually change it. If you want to do it for presentations, you can change how you draw out the circuit. You add a little bit of color, or you can even make it more Pennylane. We at Xanadu and Pennylane love our own branding because it looks really cute. So if you want to do that, you can try out our Pennylane stylization. But the whole point of it is, let's make sure that whatever we're trying to make matches the initial goal, or sorry, whatever we made matches what we were trying to make. And in this case, very simple, and it does. So we'll keep that there. Nice and colorful, brings a little bit of color to this black and white notebook that we're seeing. And now it's time to actually execute the circuit. So as with any other function, let's make sure no arguments here because we didn't need any arguments. And we're just going to type circuit, close the brackets, Shift Enter. And what we have here is executing the circuit, which returns us the probability of the Bell state. Now, what you'll notice here is it's an array, and you have just floating point numbers here. Now, how to read this is in lexicographical order, or kind of really in my head, the order that makes sense when you're thinking of binary, okay, plus entanglement. So what this is you have 50% probability of observing state 0, 0. So bit 0 being 0, or qubit 0 being 0, qubit 1 or wire 1 also being in the state 0, and then 0% of 0, 1 and 1, 0. And then again, to preserve probability, you got to be 100% of measuring something of the state 1, 1. Okay. And as you get more complex, it becomes a little bit harder to track, but the point is that it's in binary counting order. So I'll run it again just to prove the point and to make sure it saves. And then we're going to move on to something slightly different. And by slightly different, I mean all we're going to do now is change the back end. So if you remember, changing our back end is as simple as changing your device up here. So that's exactly what we're going to do. We're just going to go down here and write device. You can change it, the number if you want. I'm not going to bother. As in you could like do device 2, device 3, and so forth. But we're going to do QML.device lightning qubit now. This is the one that uses a C++ backend to make things more performant and support more qubits. And that's perfectly fine for most laptops at the moment, or desktop systems if you have it. with the exact same task. We're still going to create that bell state just to prove a point. And then I'm going to copy and paste this just so I don't need to type anymore right above bell state code. Control C, Control V if you're on Windows, and if you're on Mac, I think it's the command. But you'll know better than me. So here to note, we're only changing the backend from default qubit previously to lightning qubit now. And we're going to run. No errors popped up. Device seems to be created perfectly fine. Our Q node tied our circuit to it. Happy campers. Then we're going to run our circuit. And lo and behold, exact same thing. Just because you change your back end, depending on what added functionality you have, but one-to-one, you should expect the same result. Now, what we can do on top of this is like, okay, well, I get the same result depending on backend. Why would I ever change? What if I'm just using the same amount of qubits? Well, there is a slight timing thing that you can actually have fun with, which is I'm going to go back up here. I'm going to redefine my device as default qubit, rerun the tying of my device and through the Q node. I'm not going to draw again, but what I'm going to do is try and time my circuit. Now, this is where I'm having a little bit of fun. So hopefully this works. What I'm trying to do is prove a point about runtime. So in this case, our circuit is going through multiple executions for Google to actually time things. And nice, over 1,000 loops of this, we're getting execution times of about 1.19 milliseconds with some standard deviation, because things vary. Now we're going to do the exact same thing, but on lightning qubit, and instead time it here. And then now we're going to wait until it converges, but it's going to do essentially the same thing. And it's going to spit out a number for us over 1,000 loops. And what we notice is that we actually get faster runtime. We have 817 microseconds and 8 plus or minus, some standard deviation. Now in your mind, you're like, okay, 1.19 milliseconds versus 817 microseconds or 0.81 milliseconds. Not a big change. Who cares, right? But remember, the circuit that we define is like the very basic thing for quantum computing. And it's not a very heavy workload. And we've only have 2 work wires. So even with that such a small workload, we've observed a small difference. You can imagine as it scales up, one will get a much more problematic execution using default qubit, whereas with lightning qubit, it approaches something more feasible and more friendly. However, the resources that you use up for each case are different. And so sometimes default qubit is just the easiest way to prototype and to quickly test what you need to do. Okay. So I'm glad that worked well because the time it function sometimes gives me issues. But it's very fun. And I would encourage you playing around, can you make a workflow that works on one but not the other? But now we're going to move into something called shots, which is further functionality of our back ends. I'm going to copy and paste the code for the lightning qubit part and deleting comment here into now we're introducing shots. And what shots are repeated executions of your circuit. And it's most relevant when we want to think about it from an experimental point of view. So what the probabilities that we derived up here for the bell state made sense. If you did this analytically with pen and paper, the 50% on the 0-0 state and the 50% on the 1-1 state make perfect sense. However, that's not what you're going to get if you're going to a lab and you're enacting the circuit multiple times. Because quantum mechanics is probabilistic, you're rolling the dice, a physical dice, in the lab many times, and you're not going to get that exact 50% probability. Instead, it's going to converge depending on how many shots and how many measurements you make within that circuit. And so that's what we're going to test here. Same circuit, same device, but the only thing that changes is kind of like we're moving from the analytical world to the real simulated world, as weird as that is to say. So we're going to define it, no complaints, and now we're going to run the circuit. And now we notice the first time doesn't do anything. Second time also doesn't do anything. Maybe I should do more shots. Let's say 100. And here, thankfully, for my sake, that we actually see a difference in our probabilities. The 0, 0 state is measured to be 48% probable, and then the 1, 1 state is 52% probable. Let's say, you know what? Let's run it again. Oh, it changes slightly. And again, let's do it. It changes again. And that's showing you the probabilistic nature of kind of simulating the physical quantum mechanical process of having probabilistic states. Now you can add in more shots, let's say 1,000, and run it again. And you kind of like get a little bit more precision out of it by added floating point numbers. But the point is, you can have more shots and you should converge towards that distribution more readily or more reliably. Okay. And then the final thing that I want to show you is, at least for the Pennylane hands-on demo, is this idea of a subcircuit. Now, this one's a little bit more intensive in coding. So if you don't want to type this out frantically while I'm copy and pasting it from my backup notebook, we'll be sharing this afterwards, so don't worry too much. But the point is to share with you the fact that you don't need to write things line by line always from base quantum programming primitives. So like you don't need to specify every single gate in order and type things out without being able to shorten it. And so we introduce a subcircuit, which is similar to the templates that I was talking about above, which are just subroutines to make your workflow work a little bit more. So in this case, what I'm going to do is just run this code. And what I've done is I have a particular circuit, I've tied it to a device, but what I've added is this subcircuit, which is called within my quantum circuit. And what this subcircuit does is it gives multiple calls, or sorry, one call for an Rx gate, but you notice that within my circuit itself, I'm actually not calling the Rx gate, and I can parameterize, or sorry, directly, that is, and I can parameterize it so it can depend on, say, a looping variable here for I in range 2. We can change the value of that within it very naturally. We can parameterize it, and it saves us writing in the long run. And to verify that, we can actually see the quantum circuit drawn out here. And then if we want, we can enact circuit and make sure that we have the right values queued. 1.1 for our parameters, giving us the return of our probabilities of each state. So with that, I'm going to wrap up the live coding part of it. I have to take questions afterwards. But the takeaways here that I want to focus on is that we know the basics of how to work with Pennylane, and it's really just working with Python and putting in the instructions that we want, tying it to a device using a Q node, and then just hitting enter or running your script as you would with a normal function call. Whatever returns from that function call is the result of interest, and you can do with that whatever you wish. You can follow up with more Q nodes if you wish, put it into classical post-processing, anything that actually enables your hybrid workflow. You're not stuck doing just quantum. All right, so now I'm going to switch screens. Please tell me if you don't see it, but I'm going back to my slides. And this is more of a follow-up towards learning more about quantum algorithms for future speakers, but also just for your general career and interest in Pennylane. Is that I want to focus on pennylane.ai, where we have a lot of online content, documentation, and resources to further your learning process. So taking what you learned here today and furthering it by looking at our quantum codebook, which is a pedagogical resource on our website, which takes you through any of the background theory you may be kind of rusty on or unfamiliar with, whether it be quantum mechanics, a little bit of linear algebra, or quantum computing, if you're fine with those two, but not so much on the computing side. You have theory, and you also have kind of live demo-ish stuff that I showed you today, but in an automated and online form. Once you create a Pennylane account, you can access these, go through these exercises, and really start building up your knowledge base. Following that, we also have demos, which are kind of a little bit more advanced. Once you have the basics of quantum programming, you might have a use case that you're very interested in. For me, it's something like spin Hamiltonians for electronic systems. For others, it could be something like quantum machine learning or looking at encoding images. We have a lot of encoding images in quantum circuit. We have demonstrations that show you how to do that with Pennylane, with code, and to kind of emphasize why some people might be interested. It's very well built out, and we have a lot of demos available, over 170 now at this point, and growing. So once you get that point, or just if you're curious about what people can do with quantum programming right now, I highly recommend looking at our demos. And finally, and I think as a part of the challenges as a result from this presentation and the program, is our Pennylane.ai challenges, where you'll be able to challenge your Pennylane programming skills and kind of display your prowess and finally what you've learned through the code book, through the demos, and through this tutorial. So with that, thank you for your attention, and we can take some questions and kind of ramp down as need be.
Oh, thank you so much, Ben.
You're welcome.
All right, so let's see what's coming in on Discord. Oh, hi, Catalina.
Hi, I'm here jumping in. There have been a lot of questions on Discord.
Oh,
So I'm also at Xanadu. I'm here to help answer your questions. So maybe I can just look at them and give you a little bit of an insight of some of the questions that have been going on. So some of the questions have been around, how do I make sure that the device, like that I'm choosing what device, or the circuit knows what device to use, right? So if you maybe want to go back to the code, Ben, I think that would be the easiest way to answer the questions, because that's what more people have been asking about. If you want to even zoom in a little bit, then we can make sure everybody can see.
Sure, that was
Control plus should work. Exactly. So this is the key. I think the cell number, I don't see the number, but the one in the middle is the one that everybody should look at. The first key is if you want to run on a device, right? Then you'll specify it with this @qml.q node. So if you add this line right above the definition of your circuit, that's what will tell your circuit where to run. If this @qml.q node, you added it somewhere else, then the circuit wouldn't know where to run. But this line @qml.q node, that's like a signature here. So it really is able to glue, as Ben mentioned before. So it glues the device to the circuit. You can think of it this way. It tells the circuit where to run. And then this device, you can define it in different ways. So here we have 1,000 shots. You could decide not to add any shots, right? So if you have no shots, it's the analytical value. Let's say the theoretical value, right? So unless you specifically need shots, it's perfectly okay and perfectly fine to use no shots. I know this is different from other tools and other libraries, but if you choose not to use shots, that's totally fine. And it will give you the analytical value, basically the value if you had many, many shots. And the more shots you have, the closer you will get to that analytical value. So this answers a couple of the questions that we had here. What happens if you change the device? Do the probabilities change? Not really. It's, all being, it's randomized. So in this case, there's NumPy running this random, let's say the random shots in the backend. So it will just use the random NumPy. If you change this to default qubit, let's say the randomness would be the same. The specific numbers are different. So every time you run this cell, the specific, output for the shot changes. But overall, let's say the distribution is the same, right? Now, if you wanted to have no randomness, let's say you wanted to have the same output every time, then you would have to use a seed. So in NumPy and in JAX and in other platforms, other libraries, depends on what you want to use here in the backend. So you can also use JAX and so on. Then you would have to set the seed. This makes sure that the initialization for that randomness is always the same, so that you can get the same output and it's reproducible. So it is recommended, if you are using shots, that you use a seed so that you can always compare the results. Now, if you do not want randomness at all, then you can just use the analytical value. You don't have to use shots. And so hopefully this answered a couple of the questions. There were some questions about the drawing. So maybe you can go to the drawing section. One of the questions was, what are these parentheses for, right? So you have draw PL, you have your circuit, you have your style, which is optional. And then you have these empty parentheses there. So if you had parameters, for example, let's say your circuit would take an angle or a data point or something like that. So then in the drawing, that's where you would add, in these parentheses, that is where you add the parameters. And that semicolon at the end, that's just so that you don't print the text that talks about the figure, so the axis and the sizes. So I don't know, Ben, if you want to remove the semicolon and show people what shows up. It's nothing major, but it's just talking about the figure is usually information we don't care about. So you can totally ignore the semicolon, but it's just for a nicer print. Oh, there have been a lot of recent questions since I started talking. But let me see. What happens if, okay, why do you get probs of wires empty instead of an array? I'm not sure what the question is. So Islam, if you want to like rephrase that. Can we practice the coding on Pennylane.ai? Yeah, so the codebook, which which Ben mentioned on Pennylane.ai, that's a really good way to practice with guided exercises. So here you have a description which says, try this, and then in this little code section, then you can code there and run. If you want to also practice on a different, let's say, on your own laptop, you don't have to use Google Colab. This is just a quick way to use it. So you can use your own laptop if you prefer. But here in the code book, you have guided exercises that you can run there. Now, if you're gonna do your own project, I wouldn't recommend that you do it in the code book. The code book is more for these exercises. So you can use either your own environment on your computer or Google Colab or QBraid. QBraid is also good. So I can also recommend that you use QBraid if you prefer, if you want to maybe do something else aside from these exercises. Do we have a demo on finance in Pennylane? Don't think we have one on finance, but you can adapt the demos that exist. We have different data sets that are in the demos, and then you can adapt them to your own data set. Or if you have a finance data set, you can adapt it to that. How many qubits can the simulator support? That's an excellent question. Really, really good. It depends, because it actually depends on your computer or wherever you're running. At some point, if you try to run, let's say, 1,000,000 qubits on your computer will not be able to run that, no matter how efficient your algorithm is, right? It will just run out of memory and so on. So yeah, it will depend on your computer. Now, a good way of thinking about it is usually 20 qubits is the maximum you can run on a laptop with like a normal circuit. If you have maybe a little bit more depending on your circuit, and if you have a cluster or something, or if you're doing some kind of optimization. So we have, for example, an optimization package that allows you to optimize circuits in a certain way. You can run up to thousands of qubits, sorry. But this is like a very specific scenario. So for a ballpark number, if you want to get an overall sense of how many qubits you can run on your laptop, I'd say 20 or maximum 25, I would say. But it will depend. It will depend on what you're running and how optimized it is and what kind of packages you're using. So depending on what you're using, you can get to 25. We have run simulations with, I don't know, but a lot more, let's say.
Yes. So maybe I'll add in a little bit. Like a rule of thumb that I have in mind is for default qubit, best to stick around that 10, 15-ish range, because that's really for fast prototyping. If you're concerned about, say, the 20, 30, maybe pushing mid-30s, then you're starting to use the Lightning high performance ones. So for lightning.qubit, let's say rule of thumb 20-ish. If you have access to HPC clusters that are integrated well, you can probably push 30 and upwards. Once again, highly dependent on your workflow.
Yeah, exactly. So you might need to use some advanced tools for that, but you can always ask us. So the discussion forum is the best place. I don't know if you have the link there somewhere, Ben, but that is the best place to ask questions and so on.
I can demo the site quickly now if people want that. So here's the codebook, as mentioned. If you go to our landing page, you can look through our various offerings. So in why Pennylane. We have features, demos, compilation datasets, and so forth. If you're looking for devices specifically, you're looking for our simulators, and you can go through each of them and ask, well, which one's most fitting for me? If you need further support above that, we can go to ecosystem, and you can look at our blog, for instance, where we have a lot of information on like the recent happenings, but also, as Catalina was mentioning, our support for our discussion forum, which is everywhere here. You can sign up or log in, depending if you're a Pennylane user already, and ask questions there.
Yeah, awesome. Ben, we have a question for you.
Oh, okay. What's up?
How's your expertise in experimental condensed matter coming handy at Xanadu?
Good question. I think it's the physics background and physics curiosity that drives my main role here. It's less using my experimental background. So, fiddling with gas valves, using liquid nitrogen, that's less relevant nowadays. But most relevant is my programming of devices within the lab. That, because we're working in a Python environment in Pennylane, translates essentially one-to-one. I'm very comfortable with learning that. And also being generally familiar with the quantum materials and quantum mechanics has helped me a lot just in absorbing everything that I needed to learn.
Nice.
But great question.
Yeah. And so we have a few questions about hardware and so on. So can Pennylane be used to run circuits on quantum devices that Xanadu has? Not really. So in the past, yes, but not really. And Xanadu's, we have one computer online, but it's very, very limited. So it's not really accessible for public use. So the quick answer is no. In the future, yes. So as we're building more devices, we do want Pennylane to be able to be used there. So Pennylane can be used in other platforms. So you can use Pennylane to run on IonQ devices or IBM devices, or there are others that we're working with where we have a plugin so that you can use Pennylane and then run in different kind of devices. But interestingly, Pennylane is not currently, let's say, running on our devices because they're a little bit older. So as we develop new devices, the hope is that Pennylane, we are working to make sure that Pennylane can be run on the new devices that we're building, but it's no longer compatible with the old devices that we have, if that makes sense, hopefully. And then this connects very well to some other question that we got about how Pennylane connects with the hardware part task and so on. So remember how Ben created a Lightning qubit device and a default qubit device. These are simulators, right? So default qubit is good as a default, so you can always start with that. And as you scale a little bit, Lightning qubit, actually you can even use it from small. If you want to just forget about everything and choose one, you can also use Lightning qubit. If you decided to use actual hardware, then you would need to, for example, if you want to use IBM's hardware, you would need to get their own API key and so on. So you would need to create an account with them and get their key. And we have documentation and demos and so on that show you what you need to do to create the Qiskit device. Basically, it's called IBM Q something. You can also use Qiskit Air. So you would, instead of writing default qubit, you would write something like Qiskit Air or something like this. And I don't remember the exact name, but if you have questions, you can ask it in the forum, and then we can let you know what it is, or you can also look it up in the documentation if you prefer. But there's like a specific line. It's like one line of code that you have to write, and that's it.
To demonstrate that, here we go. You have that one line of code as promised. Is that really Pennylane is like a backend agnostic? You just got to choose the right backend that you're interested in. So in QML device, instead of default qubit, put in your Qiskit Air and you're done.
Exactly. And if you wanted to run on actual hardware, there's also this like one line basically, or two. There was a question about time limit to use Pennylane. So remember that Pennylane, if you're using the simulators like default qubit and Lightning qubit, that's running on your computer. So infinite time, as long as your computer holds, right? So usually the limitation would be, if your circuit is too big, then you'll get tired of it, right? So you'll need to optimize it. But you don't have a limitation. Pennylane is open and free. So the reason is for us, it does, like, you know, we want to make this open and available to people everywhere. Now, for the hardware, that's going to be a different story. For our newer devices, they're not going to be free, I think. I mean, I'm not the CEO, so that's not up to me. But for now, the software, I mean, the plan is for the software will stay free, right? It is Apache 2.0. That means you can actually make a copy of Pennylane. It's on GitHub. You can make a fork, a copy, and you could build a startup and sell that if you want that. That would be fine as long as you keep the line that says this is Pennylane. This was made by Pennylane, basically. As long as you keep the license, like the notice, whatever the license says, that's fine. And there are startups, and we're really happy about that because it means our, you know, what we have built is valuable for people. Some of them, they have built startups and projects based on it, and you can charge for that if you want. So there are companies that build like a startup finance layer on top of Pennylane, so that people could use it for finance. So we're not experts in finance, but they are. So this is totally fine. Pennylane itself is free, and then once the hardware is ready, that probably won't be free. Hopefully you'll, you know, this is not new here in this field, right? How does the program know how to install or recognize Pennylane? So every time you see this QML, right, QML.device, QML.header, QML.cnode, that's pulling it from Pennylane. So remember, we imported Pennylane as QML. So this is how everything connects, right? This is how it recognizes that everything is Pennylane. And yeah, we've got a lot of good comments for you, Ben. And I
Okay.
think it's time, so I want to head it over to Womanium and Wiser. I don't know if you have any final comments or so on.
This was a really great session. Thank you both so much. Thank you, Catalina. Thank you, Ben, for your time. I'm going to hand over to Abhinaya to close up.
Yeah, again, thank you, Ben. Thank you, Catalina. And thank you so much for taking the time to participate in the program and share the knowledge and use of Pennylane with our participants. We really appreciate it. Yeah.
Happy to be here. Thank you.
Again.
Great.
Yeah.
Thank you, everybody, for the questions. They were excellent. Keep them coming.